Alright, so we're going to look at limits of piecewise functions today. Piecewise limits, which we've already seen some examples of that on the problems that you did out of the book, where they're just functions that are divided into different pieces. And if you see a jump, then the limit doesn't exist. If you see a hole without a jump, then the limit does exist. Or anywhere on the function, the limit still exists. Okay. So on a piecewise limit, what you can do is figure out if there's a limit or not just by plugging in the dividing point into each equation, each piece. Okay, and then if they come out equal, then that's your limit. If they don't come out equal, then the limit does not exist. Okay, because remember, when we're plugging in, we're finding the y value. So if those y values are different, that's where there's a jump and the limit doesn't exist. Okay. So, for example, we have f of x is equal to 3 minus x for x is less than 2, and x plus 1 for x is greater than or equal to 2. Now remember what this is for piecewise functions. This section over here on the right is just telling you where the graph is split. Alright? So this is the line 3 minus x, but only up until you get to x equals 2. And then after that, it's the line x plus 1. Alright? So if we want to see if this limit exists and what it is, then that's pretty easy. We just plug in 2 into the function. So 3 minus 2 gives us the y value that this hits, which is 1. 2 plus 1 equals 3. Those are different, so the limit doesn't exist. Now that part of it's kind of easy. The graphing is what's a little bit of a pain, but it's good practice, so we're going to still do it. All right. So let's graph this. Now, when you graph a piecewise function, the best thing to do is to figure out first where you're dividing the graph. In this case, that's at x equals 2. Okay, I like to put a dotted line in there just to make it easier for myself. Now, we need to know, it's important to know where each of these functions hits that dotted line, because that's going to tell us if we have the limit or not graphically. So in order to do that, again, all you have to do is plug in this point over here into this, okay, for each one. So for this first one, we already did that. We got 1. That's the y value. So we have the point 2, 1. Now we got to decide whether to put an open or closed circle there. And this one's going to be open. This one's going to be open because there is no equal sign right here. All right. So there's no equal sign there. So that goes up to 2, but not including 2. So we got an open circle there. Okay. And then we're gonna from there we're gonna draw this to the left, because this is the left side of that line. So the graph 3 minus x is just a line with a slope of -1. That means a slope is going down. It doesn't have to be perfect, but just make it so you have a -1 slope. The line's going down and hitting that point. Okay? And then we do the other side. So the other side is the function x plus 1. When we plug 2 into that, we get 3. So that's the point 2, 3. And that's going to be a closed circle because of this equal sign right here. That's a closed circle. And that is the line x plus 1. That's a slope of 1. Okay? It's a slope of 1. That's in front of the x. So that's just going to look something like that. And then you can see graphically that the limit doesn't exist because there's a jump there. And so that's all really we have to do for that one. Let me do another example here. F of x equals x squared minus 2 for x is less than 3, 4 for x equals 3, and 10 minus x for x is greater than 3. We have 3 lines here, but it's still only one spot that we're dividing the graph. That's at x equals 3. This middle line here, where we have just the function 4 when x equals 3, all that does is tell a point, a separate point. Okay? So it just gives you a value to put a closed circle on there, because that's where the equal is. That's where the equals is. Okay? So if we graph that, the dividing line is at 3, and so this first part is a parabola, x squared minus 2. That's to the left of this dotted line. We're going to use that parabola. In order to figure out where it hits the dotted line, we're just going to plug in the 3 into that, and we get 3 squared, which is 9, right? Minus 2, that's 7. So that's the y value that this hits. So 3, 1, 2, 3, 4, 5, 6, 7. And that is going to be an open circle there, because there's no equals with it. And then what we have is this parabola. So it's a parabola facing up with a vertex at -2. So we just draw that parabola, but we stop there because the graph of that parabola has to stop right before 3. Okay, so it goes up to 3. Now the middle one here is just a point 3, 4. So that's an actual point 3, 4, and that's a closed circle because that's where the equals is. And then this last line is for the part that's to the right of this dotted line at 3, because x is greater than 3. And so we plug that in and we get 10 minus 3 equals 7. Okay, well that's the same y value as where this open circle was here. So we're going to start from there, and we have a slope of -1. Okay, so slope of -1. So it's just going to go down like that. When you're graphing these lines, you don't have to worry about the y-intercept because we're not concerned about that. You just find the point that it hits the dotted line and do your slope from there. Okay, so that's our graph. Now, does the limit exist at x equals 3? It does, because if we look at both sides, if we approach 3 from the left and from the right, we hit the same y value. This doesn't matter for the limit. That extra point doesn't matter for the limit. We're approaching the same y value from both sides, so the limit does exist, and it is 7, which is the number that we got here and here. So to answer this, you don't have to graph it, and just the graphing is just for good practice, okay? Because you'll have to do this graph it for other stuff. All right. Is that all we need for that? Yeah. Okay. What does this point do? Well, this point, it doesn't do anything for limits. But if you were asked what f of 3 is, that's the function value. That's the any closed dot or any part of the function at x equals 3. So that would be 4. But that doesn't have anything to do with the limit. Okay. All right. So there's a few problems for you to do on your homework on page 823, 37 to 40. But I'm going to give you an extra one here, so copy this down, because the ones in the book aren't all that interesting. So we got f of x equals cosine x for x is less than 0, x plus 1 for 0 is less than or equal to x, which is less than 1, x squared for 1 is less than or equal to x, which is less than 3, and 12 minus x for x is greater than or equal to 3. So this one's going to be a little bit more interesting, a little bit harder to do, because you're dividing this graph at 3 points. You're dividing it at 0, you're dividing it at 1, you're dividing it at 3. And when you're testing out the limits, you only care about each pair. So for the first pair of functions, you would plug in 0, because that's what splits those two. For the second pair of functions, you would plug in 1 because that's what splits those. And then for the third pair of functions, you would plug in 3 because that's what splits those. Okay, so have some fun with that.